Congratulations, you've made it to the final lecture for GIS 101. We're going to look at chapters 11 and chapters 13 from the textbook, and then you guys can start preparing for your final exam. So if we think back to, getting data from space and what remote sensing is and how that all plays into GIS, it's essentially collecting information from a distance. And that distance has changed over the years, from the turn of the century, taking pictures from hot air balloons, up through taking pictures with satellites in the 50s and 60s, to the space agency being formed in 58, the Corona program running in the US in the 60s, all the way up to 72 when the Corona program itself stopped, and we then had other spying satellites, to all the remote sensing satellites that are currently in existence. So let's talk about the satellites in orbit. So some satellites are geostationary, and what that means is it rotates at the same speed as the Earth over the same space, and it basically doesn't move. It just sits there and looks straight down over a certain area. Some satellites are what they call near polar, and that means that it roughly rotates north pole to south pole several laps per day. So what happens is each path around the Earth covers a narrow path wide, but over a long distance. And as the Earth turns, the rotation of the satellite from pole to pole maintains its same position, and so the Earth moves underneath of it. So each new pass, that swath that it collects, is somewhere new. And after a certain number of days, all the paths will have lined up and you will have taken a complete picture of the Earth. Then there's sun-synchronous orbits. These paths go over the same location at the same time every day. And this allows you to have the exact same lighting on a day-to-day basis. One of the more common remote sensing satellites is the Landsat satellites. And the Landsat satellites make rough to 8 to 14 near polar rotations per day. And each of these paths is roughly 185 kilometers wide. So when we think about Landsat, it basically does something like this. It's on this near polar orbit, going around the Earth as the Earth's turning. It's measuring and collecting information 185 kilometers wide, and then the Earth turns. When it makes the next pass, it takes another one. Now the two paths don't connect, okay? There's going to be a big gap in between them, and in between the second and the third, between the third and the fourth, between the fifth and the sixth, etc. But over the course of days, all the spaces between the initial passes get filled in, and then after a certain number of days, you have total coverage. And so it looks kind of like this. You can see on day one where you go, middle of the country. Day two, you're a little further west. Day three, you're more towards the Pacific. Day four, you're back in the Midwest. Day five, you're back out west towards the West Coast. 6, you're closer to the east. 7, you're back to the west. 8, now, so 8 days later, you get the path that lines up next to your first pass. And then 9 goes back in, and 10, 11, and so on and so forth. So that after a total of 16 days, you covered that entire section that you see there. Now, next to that pass, on either side, there's another selection like that, if you will, going on. So that basically, about every 16 days, 2.5 weeks, you get complete coverage of everywhere. The sensors in these remote sensing satellites generally come in two different types. One's called an across track scanner and one is called an along track scanner. These are commonly referred to as a whisk broom and a push broom. The whisk broom goes side to side, the push broom goes forward. So the way it works is, with the across track scanner, you've got a rotating mirror and a detector. The information comes in that it sees from the ground, hits that rotating mirror, and as the mirror rotates, it basically scans across the path, bounces that signal to a single detector, and then that detector converts all that information and sends it out in the satellite signal. The along track scanner has an array of detectors. So instead of scanning across at one time, the along track scanner scans continuously in a straight line for each of the detectors. So what does satellite or remote sensing imagery look like? Well, here we have the same location at 3 different resolutions from 3 different sensors. As sensors have more and more coarse resolution, it's harder and harder to make out specific details. But it would work perfectly fine for looking at larger things like, how much of a forest is covered in leaves, how much land is vegetation, how much is urban. If you imagine zooming out far enough, that far picture on the left would eventually make sense as sort of what you're looking at. The one in the middle is kind of in between. You can identify some features, but not with much detail. Whereas on the one on the right, you get higher and higher resolution, you can see more and more detail of what's actually in the image. Now we have the same location. Let's look at changes in pixel depth. Pixel depth has to do with what information is stored. And it's a sort of a complicated thing, but essentially 2-bit, 4-bit, 8-bit. It has to do with whether you're selecting different numbers of and how much range of value you can collect. And so at 2-bit, not a lot going on. At 4-bit in the grayscale, a lot more variability, and at 8-bit, even more. And essentially what we're doing here is trying to differentiate the amounts and types and kinds of energy. That's my abbreviation for energy, by the way, NRG, that we see either reflected or absorbed from the land below. Historically, if you look at the Landsat program, first one went up in 71 or 72, 75, and then 78, and then those were relatively short satellites. Satellite technology improved by 1982 when Landsat 4 was launched, and then in 84 when Landsat 5 was launched. You see they have a lot longer lifespan. You notice that there's not a Landsat 6. It blew up on launch. In 1999, Landsat 7 was launched. And notice how it's kind of got some breaks out there at the end. There's been a couple issues with some of the newer satellites in terms of what they're collecting and when, but they're basically still going, at least as far as we know. Within the individual satellite, they collect different bands of information. And what a band is a range within the electromagnetic spectrum that an individual sensor selects. Okay? So for example, if we're looking at this particular satellite, it's collecting 11 bands of information. Band 1, it has a couple of different sensors. Well, it has, okay, so let me back up just to make sure I don't confuse you guys with this. So let's look at um, the first satellite. So uh, going across, you see the different ranges that things collect for band 1, for band 2, for band 3, band 4, etc. Up to down, we have the OLI and the TIRS, that's the satellite. We have the RS sensor. We have the ETM plus. That's a newer type of thematic mapper. We have the TM, which is the thematic mapper, and then some of the older sensors were the MSS sensors, 1, 2, 3, and MSS 4, 5, and 6. And these different sensors are in different satellites. And so what's band 1 in one satellite might be the same as band 2 in another. But in general, just to give you some idea of what some of these bands might be, if we're looking at the satellites that have the OLI and the TIRS sensors, with 11 bands of information, you get a 0.43 to a 0.45, which is a sort of a narrow blue. They call it a coastal blue. Then you have a blue, 0.45 to 0.51, a green, 0.53 to 0.59, a red, 0.64 to 0.67, a near infrared, 0.85 to 0.88, a shortwave infrared, 0.157 to 1.65, a second shortwave infrared. Then you have a panchromatic, which is everything from 0.5 to 0.68. You have a Sirius, 0.136 to 138. You have a thermal band, which is even further up, 10.6 to 11.9, and a second thermal band. All of these allow you to look at and identify how things react in different frequencies. I'll give you an example. If you're looking at water and you're trying to decide how clear the water is, stuff that's in those various bands of blue will help you determine that. When you're trying to look at the health of vegetation, using the near infrared along with the red and the green can help you determine the health of it. If you're trying to look at things after a fire to see where hot spots still remain, the thermal bands are actually pretty helpful. If you're trying to determine the difference between things like brown rocks and brown dirt, and you take a pass at night, the rocks have a more dense surface, or they're a more dense material, so they should hold thermal energy longer, so they should basically in the thermal glow at night compared to the surrounding objects. Lots of unique and different ways you can use these bands to identify stuff, and that's what remote sensing is all about. Here is what one of those Landsat satellites looks like up there in space, lapping around the planet. And here is an example before, during, and after a fire. And you can see where the fire is at. When you look for remote sensing data, there's two things you need to know. First is the path number, and second is the row number. Think of it as a kind of irregular shaped grid. The path is the satellite path around the globe. The row is how far north or south you want it. And essentially, once you figure out locations in a certain path and in a certain row, that row path combination is the data that you're looking for, and there'll be a bunch of it, but it won't be like in continuous days. It'll be like you have some on the 1st, you have some on the 16th, you have some on the 2nd of the next month, and so on and so forth. And depending on things like cloud cover and the frequencies that you're looking at, you may end up having to get data over the course of several months. And so it's not always ideal for every situation. USGS has a global visualization viewer that allows you to look at some of the spatial data. There's lots of these out. They change pretty frequently. They're always updating this stuff and making it available in new and different ways. But in general, remote sensing usually requires more specialized software. There is ever increasingly more things you can do in ArcGIS relative to remote sensing, but it's not specifically designed to work with this data. But it has some tools and some very sophisticated tools to do so. Whereas remote sensing software is nothing but tools to do these things. And so not only can you do some stuff, you can do a wide range of things with the remote sensing data. And here we can have some more information, and you can see how things would change and look differently over time. Next, we're going to talk about Chapter 13, which is digital landscaping. First thing we got to talk about is a z-value. A z-value, just like x, y, z, x and y are physical locations, z is elevation. So it's the coordinate that gives us the third dimension. We'll also, from time to time, you'll hear about a vertical datum. This is where your zero elevation comes from. On topological maps, they show landscapes and terrain. We have DRGs, which are digital raster graphics. This is what happens when you take a topological map and you scan it into an image. There's also things like geotiffs and tiffs and images. But a geotiff specifically is a tiff, which is an uncompressed format for an image. But what separates a geotiff is it has spatial information. And of course, the one that most everyone's familiar with are contour lines. And this is a map that uses lines at consistent intervals of elevation so that you can see how elevation changes and things like that. This is not what you probably think it is. You probably think this is an oblique view of some mountain that was taken with a camera. This is a satellite photo from above of this area that has been draped across a three-dimensional model of the mountain to generate this, a virtual three-dimensional GIS landscape. Some more examples. We're looking at Youngstown, Ohio. We have DLGs, digital line graphics. And then on the right, you've got a more traditional looking digital raster graphic of some sort. Here is an example of contour lines. And basically, this is just a map of a location somewhere. And each line represents a change in elevation. It's typically something like, I don't know, say like 20 meters, 40 meters, somewhere in that range. You can figure it out by counting the number of lines between the two numeric values. And you can see how every once in a while on a line, they're darker, and you see like, it'll say 1700. And you have a dark line, and then another dark line, and you're at 1900. So from one dark line to the next dark line, it's basically a change of 100. And so between two dark lines, you have 1, 2, 3, 4. You have 5, steps. And so that means that 100 divided by 5 is going to be 20. So for every line that you go up or down, it's a change in elevation of about 20 meters. And so this allows you to see things like not just how high or low something is, but you can also see sort of the configuration of the various ridges and valleys along the sides and how steep things are, because when things are steep, the lines are close together, and when things are not steep, they're further apart, like at the top left-hand side of the image where you can see that things are really stretched out. It's because it's relatively flat. Some of these things get pretty intense with the information. This is, I believe, a geotiff, and there's a ton of information on there, and that does not necessarily make it easier to understand. They're actually quite complicated, and reading maps like this is a skill in itself. So let's talk about some of the elements of these maps that are important. The map color is sort of that border around the outside, the white section on that previous map. And it's filled with information on a USGS topological map. If we talk about a DEM, that's a digital elevation model, that's a raster of elevation values. A DTM is a digital terrain model. That is a raster of elevation data for the surface of the Earth. And so we strip away all the man-made features like houses and roads and things like that. And we fill in those holes based on the surrounding values that we know are Earth. Then we have digital surface models, a DSM. This is an elevation model of the surface of whatever's there. And so that's the top of your house, or the top of your car parked in the driveway, or the top of a jogger running through your neighborhood when they shot the LiDAR, or whatever it is. Collectively, there's a national elevation data set that USGS has called the NED, the National Elevation Data. A viewshed is similar to a watershed, with a watershed being everything that drains to a point. A viewshed is everything that can be seen from a point. We also talk about some primary terrain variables like slope. And slope is the rise over the run. It's the change in elevation over a linear distance. So if you imagine going out some direction 50 feet, it's how far up or down did the elevation go. And you can measure that in percent or degrees. Aspect is simply the direction of the steepest slope from any one location. So imagine you're standing somewhere, look around you in 360 degrees, figure out where it's the steepest, either downhill or uphill, and whatever that is the direction of your aspect. In other words, that is the direction that your slope is facing. Your hillshade is essentially just fake shadows with a fixed sun position, and we use that because hillshades actually make 3D surfaces look more realistic. So if we're thinking about how this kind of works, we got to remember that we can't really truly have 3D stuff because we have a 2D screen. So what we do is we make something that looks three-dimensional. It's a trick of how we visualize things. We look at it from sort of these odd angles, and we have these isometric drawings that are designed to make it look 3D. And so we have a real 3D object, but we view it in 3D-ish, and a lot of times that's referred as 2.5D. This is an elevation model of a location, and this particular one, I believe, is a 10. A 10 is a triangulated irregular network. It's essentially a vector elevation model, and it is made up of tiny little triangles that connect to form the surface of the location. Not all remote sensing happens from satellites. Sometimes it happens from airplanes, and here's a nice little whisk broom scanner mounted in an aircraft taking lower elevation data collection and remote sensing, and this allows you to get a lot more detail free from a lot of interference. Now, to do this though, you need to know the exact position of the aircraft, the exact direction of travel, the exact direction that it's pointing, and then its sort of three-dimensional configuration in the air, how it's leaning. And so it takes an inertial monitoring system to understand all that, and a GPS to understand all that, and then a gimbal gyroscope based kind of setup to understand the actual position of the aircraft, because it has to know everything in order to know the location of the stuff that it's mapping. Digital elevation models and all this stuff is actually quite impressive. You can generate some really amazing things from satellites and aircraft. This overhead is a really famous volcano, Mount St. Helens. It's the last sort of major eruption in the U.S. in a semi-populated area of Washington State. And the entire side of the caldera blew away. And so it had a pretty dramatic effect. And this is what it looks like if you strip all the vegetation away and just look at it. So just kind of review a little bit what we were talking about. Digital elevation model is terrain elevation. So this is the Hawk DEM, and you can see the look there. And as the values get darker, it's lower. Lower would be like the stream bottom. The white is the edges near the top. That's going to be the ridge lines. The next map from that DEM and those elevation values, we calculate slope. The more green it is, the flatter. The more red, the steeper. And so you can kind of see how um, you have these flat sections on top of the ridges that turn into these red and yellow sections on the side that go down to a stream that turns into more of a green color again, that all drains together into the big water body. And then looking at each of these little individual nooks and crannies, if you will, you can think about the direction that they're facing, and that would be what aspect it tells us. And so for each of these colors and aspects, you can tell whether it's pointing north or east or south or what have you.